Imagine standing at the edge of a cliff face 80,000 years ago. The world spread before you is unrecognizable. Vast stretches of savanna and forest, untamed by human hands. Your breath forms clouds in the crisp dawn air. Behind you stands a small band of humans, perhaps 30 in total. Their faces marked by hardship and hunger. The children's ribs show through their skin. The elders' eyes hold a weariness that transcends ordinary fatigue. They are your people, your entire species, and they are all that remains. This is not a fictional apocalyptic scenario. This may be our actual history, a moment when humanity stood at the precipice of extinction, reduced to perhaps fewer than 1,000 breeding individuals worldwide. The genetic evidence is compelling. Around 80,000 years ago, something catastrophic happened to our species, an event so devastating it nearly erased us from Earth's narrative. A bottleneck so severe that all non-African humans today descend from just a handful of survivors. What could bring a resourceful, intelligent species to the edge of oblivion? What force of nature could so thoroughly decimate our ancestors that their total population fell below the number of people in a small, modern apartment building? Tonight, we explore humanity's closest brush with extinction. The night our species almost disappeared, we'll examine the mounting evidence from genetics, archaeology, geology, and climatology that tells a haunting story of survival. The journey takes us from the massive Toba supervolcano eruption to genetic markers in your own DNA, from ancient climate records trapped in ice cores to the dispersal patterns of early humans across a changing landscape. We'll explore competing theories about what triggered this bottleneck. Was it the after effects of the largest volcanic eruption in 2 million years, a pandemic, climate change, or something else entirely, something we haven't yet considered? The answers matter not just for understanding our past, but for confronting our future. Human resilience in the face of catastrophe offers lessons for our species as we face new existential threats of our own making. Consider this: every human alive today, all 8 billion of us, shares a genetic legacy shaped by this near-extinction event. We are all descendants of the few who survived when the vast majority perished. What were they like, these ancestors who endured? What knowledge and adaptations allowed them to persist when others failed? What decisions did they make that inadvertently preserved our entire species? The story begins with a paradox that has long puzzled scientists. Despite being the planet's dominant species, humans display remarkably low genetic diversity compared to other mammals, even endangered ones. Chimpanzees living in a single forest possess more genetic diversity than all 8 billion humans combined. This lack of variation suggests a severe population reduction, a bottleneck, in our recent evolutionary past. Something happened, something that nearly ended us. Throughout this exploration, we'll examine the scientific evidence dispassionately, but we'll also acknowledge the profound implications. This isn't merely academic history, it's the story of our collective survival. If you've discovered your own ancestry through genetic testing, you've glimpsed the shadows of this ancient catastrophe. The markers in your DNA contain echoes of these events, like cosmic background radiation from the Big Bang. The genetic threads connecting all non-African humans today converge on a remarkably small founding population. These individuals, perhaps numbering only a few hundred breeding adults, became the ancestors of billions. Their story is one of extraordinary resilience in the face of apocalyptic conditions, surviving on a planet suddenly turned hostile. A testimony to human adaptability when confronted with circumstances that drove countless other species to extinction. As we explore this existential crucible, we'll encounter questions that transcend science. Questions about meaning, purpose, and the fragility of our existence. Questions that remain relevant as we face new threats to our survival. In the coming hours, we'll examine the multiple lines of evidence pointing to this bottleneck. We'll consider alternative explanations, weigh competing theories, and explore what this ancient catastrophe reveals about our species. The journey begins 80,000 years ago, when Homo sapiens was just one of several human species walking the Earth. We were not yet dominant, not yet spread across every continent. We were simply struggling to survive. Let us travel back to that precarious moment when our future hung by the thinnest of threads. when our entire species nearly joined the long list of evolutionary experiments that nature tried and discarded. This is the story of the night humanity almost disappeared. Chapter 2. The Genetic Memory of Catastrophe. The human genome is a historical document written in a 4-letter alphabet spanning billions of characters. Each of us carries this text within every cell of our bodies, an unbroken narrative connecting us to our most distant ancestors. Within this text lies evidence of a catastrophe, a moment when our genetic diversity collapsed. The bottleneck appears in our DNA like a scar, visible, undeniable, yet mysterious in its specific cause. When geneticists compare human DNA to that of our closest relatives, something immediately stands out. Chimpanzees, with a global population of roughly 300,000, possess substantially more genetic diversity than all 8 billion humans combined. This counterintuitive finding puzzled scientists for decades. How could the planet's dominant species, spread across every continent and ecosystem, show less genetic variation than a species confined to small regions of Africa? The answer appears to be a population collapse of staggering proportions, a near-extinction event that eliminated the vast majority of human genetic lineages, leaving only a small fraction to repopulate the Earth. By analyzing mutation rates and genetic variation, scientists estimate that around 80,000 years ago, the total human population crashed, perhaps to fewer than 1,000 breeding individuals worldwide, possibly as few as a couple hundred. For context, the International Union for Conservation of Nature classifies any species with fewer than 2,000 breeding individuals as critically endangered. Humanity, by this standard, would have qualified for immediate conservation intervention. The implications are profound. If these estimates are accurate, our species came perilously close to joining the 99.9% of all species that have ever existed and subsequently gone extinct. We nearly vanished before developing civilization. By the way, do you ever wonder how close your own ancestors came to being among those who didn't make it? The thought that any of us exist today seems almost miraculous considering these odds. The genetic evidence appears in several forms. First is the remarkably low nucleotide diversity across human populations. The average genetic difference between two randomly selected humans is just 0.1% of our genome. Second is the pattern of linkage disequilibrium, the non-random association of alleles at different genetic loci. This pattern suggests a severe recent bottleneck affecting all non-African human populations. Third is mitochondrial DNA evidence. Mitochondria, the cell's power plants, contain their own DNA passed exclusively through maternal lines. All living humans trace their mitochondrial DNA to a theoretical mitochondrial Eve who lived in Africa. Similarly, Y chromosome studies trace all living males to a Y chromosomal Adam. These convergences don't mean just two individuals existed, but rather that other genetic lineages were eliminated during population crashes. The bottleneck appears most severe in non-African populations, suggesting it occurred as humans were expanding out of Africa. Those who remained in Africa maintained somewhat higher genetic diversity, though they too experienced population reductions. What makes this bottleneck particularly interesting is its timing. It coincides with several major environmental events, including the super-eruption of Mount Toba in present-day Indonesia, the largest volcanic eruption of the past 2 million years. Around 74,000 years ago, Mount Toba ejected approximately 2,800 cubic kilometers of material, enough to cover the entire continental United States in a layer 15 centimeters deep. For comparison, the 1980 Mount St. Helens eruption ejected just 1 cubic kilometer. The Toba eruption would have triggered a volcanic winter lasting years, or possibly decades. Global temperatures may have dropped by 3 to 5 degrees, devastating plant life and collapsing food chains worldwide. Ice core samples from Greenland and Antarctica confirm a major cooling event during this period. Ash layers from the eruption have been found across India, Malaysia, and parts of Africa, thousands of miles from the volcano. The coincidence between this cataclysmic eruption and the human genetic bottleneck is compelling, though not definitive. Other factors, including disease, competition with other human species, or cumulative environmental stresses, may have contributed. What matters is that something brought humanity to the brink of extinction, and a small group of survivors, perhaps just a few extended families, carried the future of our species through this existential gauntlet. The stakes could not have been higher. Had the population declined even slightly further, humanity might have succumbed to what conservation biologists call an extinction vortex. Too few individuals to maintain genetic diversity, leading to inbreeding, reduced fitness, and eventual extinction. Instead, these survivors passed through the bottleneck, carrying a reduced but sufficient genetic legacy. Their resilience enabled the subsequent expansion of humanity across the globe, ultimately leading to our current planetary dominance. This bottleneck may explain certain aspects of human psychology and social behavior. Our remarkable capacity for cooperation, innovation under pressure, and adaptation to diverse environments may be partially attributed to selection pressures during this crisis. The survivors likely possessed traits that proved advantageous during catastrophic conditions. Problem-solving abilities, cooperation, resource efficiency, and psychological resilience would have conferred survival advantages. These same traits, forged in the crucible of near-extinction, later enabled humans to colonize every habitable environment on Earth. From Arctic tundra to Saharan desert, from Himalayan plateaus to Pacific islands. Understanding this bottleneck gives us perspective on our present environmental challenges. Our ancestors survived Earth's attempt to extinguish them. We now face threats of our own making, climate change, nuclear weapons, pandemics, that could succeed where nature failed. The story of our near extinction raises profound questions. Had humanity disappeared 80,000 years ago, would another species have eventually developed intelligence and civilization? Was our survival mere chance, or were we somehow destined to endure? These questions transcend science, touching on philosophy and even spirituality. They speak to our place in the cosmos and the precariousness of our existence. They remind us that our presence here is not guaranteed. As we explore the evidence for this bottleneck and its potential causes, we confront the fragility of our species. We recognize that our current dominance masks a history of vulnerability and perhaps a future of uncertainty. Chapter 3. Before the bottleneck, the early human world. To understand the significance of humanity's brush with extinction, we must first establish what the world was like before disaster struck. The Earth of 80,000 years ago was a remarkably different place, yet recognizable in its basic geography. The continents sat in their familiar positions, but coastlines extended further as vast amounts of water remained locked in extensive ice sheets. Sea levels were approximately 60 meters lower than today, creating land bridges between continents. Most notably, the Bering Strait between Asia and North America was dry land. Australia and Papua New Guinea formed a single landmass called Sahul, connected to Southeast Asia by only a narrow water crossing. The climate fluctuated within a broader ice age that had begun roughly 2.6 million years earlier. Earth oscillated between glacial periods, severe cold, and interglacial periods, relative warmth, driven by variations in Earth's orbit around the Sun. Around 80,000 years ago, the planet was transitioning from an interglacial period toward another glacial advance. Global temperatures were dropping, albeit gradually, with significant regional variations in climate patterns. The human landscape was even more different than the physical one. Homo sapiens was just one of several human species coexisting on Earth. We shared the planet with at least 3 other human relatives. In Europe and parts of Asia lived the Neanderthals, Homo neanderthalensis, a robust, cold-adapted human species with brains as large as or larger than our own. They had already occupied these regions for hundreds of thousands of years. In parts of Asia, particularly Indonesia, lived the diminutive Homo floresiensis, the hobbits of Flores Island. Standing just over a meter tall, they represented a remarkable case of island dwarfism in a human species. And in the caves of southern Siberia and parts of Eastern Asia lived the Denisovans. Known primarily from fragmentary remains and DNA analysis, These humans were a distinct lineage related to Neanderthals. Our own species, Homo sapiens, had evolved in Africa between 200,000 and 300,000 years ago. By 80,000 years ago, we had expanded throughout that continent and were beginning tentative migrations into the Middle East and Southern Asia. The total human population, counting all Homo species, was likely quite small by modern standards. Perhaps a few million individuals spread thinly across vast territories, living in small bands of 20-50 individuals. These populations relied on sophisticated stone tools, controlled use of fire, and complex social structures. They were hunter-gatherers, following animal migrations and seasonal plant availability, with no permanent settlements. Evidence suggests early humans were cognitive equals to modern people. They lacked our accumulated knowledge and technology, but possessed the same intellectual capacity, emotional range, and problem-solving abilities. Archaeological sites from this period reveal symbolic thinking through ochre use, simple jewelry, and intentional burial of the dead. These behaviors indicate complex cultural practices and possibly religious or spiritual beliefs. These pre-bottleneck humans had already developed language, though in what form remains unknown. They crafted specialized tools, maintained fire, hunted cooperatively, shared food, and transmitted knowledge across generations. Their world was one of immediate concerns: finding food, maintaining safety, caring for young, preparing for seasonal changes. Their time horizon likely extended to annual cycles, not centuries or millennia. Disease was a constant companion, with no treatments beyond herbal remedies and supportive care. Injuries that today would be minor could prove fatal. Life expectancy at birth was perhaps 30 to 35 years. Infant mortality was devastatingly high, with perhaps 40% of children dying before age 5. Those who survived childhood, however, often lived into their 60s or 70s, serving as repositories of group knowledge. Daily life involved constant movement, significant physical labor, and intimate knowledge of local environments. Every adult possessed survival skills that few modern humans maintain: tracking, foraging, tool-making, weather prediction. Their diet varied by region, but generally included a diverse mix of plant foods, meat, fish, and shellfish, depending on habitat. This diet was typically more varied and nutritionally complete than early agricultural diets would later be. The cognitive world of these humans likely included rich oral traditions, mythologies, practical knowledge, and social histories. Without writing, memory served as the repository for all cultural information, necessitating regular retelling. Archaeological evidence suggests these humans maintained extensive social networks spanning hundreds of kilometers. Rare materials like ochre, shells, and high-quality stone moved through these networks, indicating trade or gift exchange. Climate influenced every aspect of daily life. Seasonal migrations followed game animals and plant availability. Weather determined daily activities. Climate shifts could render previously productive territories uninhabitable. This was the human world poised on the edge of catastrophe. A world of small mobile bands of hunter-gatherers, technologically simple by our standards, but socially and cognitively sophisticated, with deep knowledge of their environments. When disaster struck, these widely dispersed populations faced it with the tools, knowledge, and social structures they had developed. Some groups would survive, most would not. The bottleneck event would not have appeared as a single catastrophe, but rather a cascade of environmental changes: declining game, failing plant foods, unusual weather patterns, unfamiliar seasonal fluctuations, a world becoming steadily more hostile. Adaptation to these changing conditions would have required innovation, cooperation, and sometimes migration to unfamiliar territories. Those who could not adapt, or were simply unlucky, would leave no genetic descendants. As we examine this pre-bottleneck world, we see both vulnerability and resilience. Small populations dispersed across vast landscapes were vulnerable to extinction, yet their mobility and environmental knowledge provided survival advantages. The stage was set for a severe test of human adaptability, one that would eliminate most human lineages while allowing a few to continue. This evolutionary crucible would shape the genetic legacy of all people alive today. Chapter 4. The Gathering Storm. First Evidence of Catastrophe. The first hints of impending disaster appeared in the skies over Southeast Asia approximately 74,000 years ago. On the island of Sumatra, a massive caldera, known today as Lake Toba, began to show signs of imminent eruption. For the humans living nearby, the warning signs would have been unmistakable but incomprehensible. Increasing earthquake activity, strange animal behavior, venting gases and shifting ground would have preceded the main event. When Mount Toba finally erupted, it released energy equivalent to approximately 1.5 billion Hiroshima-sized atomic bombs. The explosion would have been audible thousands of kilometers away, creating the loudest sound heard by human ears in hundreds of thousands of years. The eruption column pushed ash and aerosols 40 kilometers into the stratosphere. High-altitude winds distributed this material globally, blocking sunlight and triggering the sudden onset of volcanic winter conditions worldwide. Archaeological evidence of this cataclysm appears in the form of ash layers. In India, scientists have discovered Toba ash deposits averaging 15 centimeters thick across thousands of square kilometers, with some deposits reaching 6 meters deep. The ash itself was deadly, toxic to inhale, contaminating water sources, crushing vegetation, and rendering landscapes temporarily uninhabitable. But the indirect effects proved far more devastating and long-lasting. Computer models suggest global temperatures may have plummeted by 3.5 degrees Celsius within months of the eruption. For comparison, the difference between current global temperatures and the depths of the last ice age is about 5 degrees Celsius. This abrupt cooling would have triggered catastrophic ecosystem collapse across much of the planet. Plant growth would have slowed or stopped entirely in many regions, causing cascading failures throughout food webs. The paleoclimate record confirms a major cooling event coinciding with the Toba eruption. Ice cores from Greenland show a rapid temperature decline followed by decades of colder than normal conditions. Marine sediment cores tell a similar story, evidence of abrupt cooling followed by a prolonged cold period. Pollen records show major vegetation changes consistent with significant climate disruption around this time. For humans living in the shadow of Toba, the consequences were immediate and devastating. Archaeological sites in India show a characteristic blank layer immediately above the Toba ash deposits, evidence of human absence following the eruption. Some researchers have found stone tools immediately below and above the ash layers, suggesting eventual reoccupation of these areas. But the gap indicates a period when human habitation became impossible in the regions closest to the eruption. The geological evidence alone paints a picture of environmental catastrophe. But the most compelling evidence for a human population collapse comes not from rocks and ice, but from our own DNA. Genetic studies using various methods converge on a striking conclusion. The human population experienced a severe reduction around this time. This appears most dramatically in the limited diversity of non-African populations. One particularly revealing study examined the diversity of ALU elements, short pieces of DNA that can copy themselves within the genome. Humans show remarkably low ALU diversity compared to other primates, consistent with a recent severe bottleneck. Another approach analyzed patterns of microsatellite variation, short repeating DNA sequences that mutate relatively rapidly. These patterns suggest an ancestral population of perhaps just 600 individuals at the bottleneck's peak. Mitochondrial DNA studies yield similar results. All non-African mitochondrial lineages trace back to a handful of founder lineages that left Africa. The limited diversity suggests very few women contributed to the founding populations outside Africa. Y chromosome studies tell the same story for male lineages. The pattern suggests that only a small number of men became the ancestors of all non-African males alive today. The geographic pattern of genetic diversity provides additional clues. Human genetic diversity decreases with distance from Africa, creating what geneticists call a serial founder effect pattern. This pattern emerges when small groups repeatedly split off from larger populations, each time carrying only a subset of the original genetic diversity. It's exactly what we would expect if tiny bands of survivors gradually repopulated the world after a catastrophe. Intriguingly, archaeological evidence suggests technological regression following the bottleneck period. In some regions, tool complexity and diversity decreased, suggesting loss of specialized knowledge when population density fell below the threshold needed to maintain it. This pattern matches what anthropologists observe in contemporary societies. Specialized knowledge requires sufficient population density and regular transmission to persist. When populations crash, complex technologies are often lost. The combined evidence from genetics, archaeology, and geology paints a compelling picture. Around 74,000 years ago, something triggered a human population collapse so severe that our species nearly vanished. The Toba catastrophe theory offers a straightforward explanation for this timing. The supereruption and subsequent volcanic winter created environmental conditions that most human populations could not survive. Yet some scientists question whether Toba alone could have created such a severe bottleneck. They note that other large mammals don't show similar genetic evidence of population collapse during this period. This observation has led to alternative theories, including the possibility that the bottleneck predated Toba. Perhaps earlier climate shifts, competition with other human species, or pandemic disease had already reduced human populations. Others suggest that Toba may have been the final blow in a series of environmental challenges, a perfect storm of climate deterioration, resource competition, and finally volcanic winter that pushed humans to the brink. The debate continues in scientific circles, but the genetic evidence for a bottleneck remains robust. Something reduced humanity to a precarious state, leaving only a small founder population to repopulate the Earth. As dawn broke on the post-Toba world, these survivors faced unprecedented challenges: drastically altered landscapes, collapsed ecosystems, and climate conditions unlike anything in living memory. How did they survive when so many others perished? What adaptations, physical, technological, or social, allowed them to endure? And most intriguingly, did this near-extinction event fundamentally change the trajectory of human evolution? The answers may lie in the archaeological record of the immediate post-bottleneck period. Evidence of new adaptive strategies, technological innovations, and migration patterns that emerged as humans recovered from the brink of extinction. But the most dramatic changes may have been invisible, genetic and cognitive adaptations that left no direct archaeological trace. Changes in our ancestors' brains, immune systems, and social behaviors that equipped them for a world transformed by catastrophe. As we'll explore in the next section, the aftermath of the bottleneck coincided with remarkable developments in human culture, including the first evidence of complex symbolic expression, long-distance trade networks, and technological standardization. Was this timing coincidental, or did the bottleneck itself reshape human cognitive and social capabilities? Did surviving the brink of extinction fundamentally change what it means to be human? Chapter 5. Contradictions in the Ashes. The Toba catastrophe theory presents a compelling narrative. A supervolcano erupts, triggers global cooling, and nearly extinguishes humanity. But science rarely yields simple stories, and the Toba hypothesis has accumulated several significant contradictions in recent years. The first challenge comes from sites in South Africa, particularly Pinnacle Point and Sibudu Cave. Archaeological excavations reveal continuous human occupation through the supposed bottleneck period, with no evidence of population crash or technological regression. At these sites, humans maintained complex technologies, including heat-treated stone tools and bone implements. They harvested marine resources, used ochre for symbolic purposes, and apparently thrived during the very period when humanity was supposedly on the brink. Similar evidence emerges from other African sites. At Blombos Cave, researchers found shell beads, engraved ochre, and bone tools dating to periods before, during, and after the Toba eruption. No discontinuity appears in the archaeological record. These findings suggest that if a population bottleneck occurred, its effects were geographically uneven. African populations may have been buffered from the worst impacts, while humans in Asia and Europe suffered more severely. A second contradiction emerges from sites in India, directly in the path of Toba's ashfall. At Jwalapuram in southern India, archaeologists discovered stone tools immediately above and below the Toba ash layer, with no significant technological change between them. This discovery challenges the assumption that areas receiving heavy ash deposits became temporarily uninhabitable. Humans apparently persisted in these regions despite substantial environmental disruption, adapting to changing conditions rather than disappearing. A third contradiction comes from paleoclimate studies that question the severity and duration of the volcanic winter. Recent climate modeling suggests Toba's cooling effect may have been more moderate and shorter-lived than previously thought. Some models indicate global cooling of perhaps 5°C lasting a decade, rather than the catastrophic 3 to 5°C cooling over centuries. This revised estimate suggests a significant but survivable climate disruption rather than a civilization-ending catastrophe. Perhaps most puzzling is the lack of evidence for population crashes in other large mammals during this period. If Toba triggered a global ecological collapse severe enough to nearly extinguish humans, we would expect similar genetic bottlenecks in other species. Yet genetic studies of elephants, tigers, and great apes show no evidence of severe population reductions coinciding with Toba. This absence suggests either that the climate effects were less severe than proposed, or that the human bottleneck had other causes. Archaeological evidence from Southeast Asia presents another contradiction. In Malaysia, stone tool assemblages show technological continuity across the Toba event horizon, suggesting that human populations maintained their cultural traditions despite the eruption. These contradictions don't invalidate the bottleneck's existence. The genetic evidence remains robust. But they do complicate the narrative, suggesting a more complex interplay of factors than a single volcanic catastrophe. If not Toba alone, what combination of factors might have driven humanity to the brink? Perhaps the answer lies in considering multiple converging stresses rather than seeking a single cause. Another anomaly appears when we examine Neanderthal and Denisovan populations during this period. Genetic evidence suggests these human species also experienced population reductions, but not as severe as Homo sapiens. This differential impact requires explanation. If Toba affected the entire northern hemisphere, why would our species suffer more drastically than our robust, cold-adapted cousins? The answer may lie in different adaptive strategies or population distributions. Further complicating the picture is evidence that multiple human bottlenecks may have occurred. Genetic studies suggest several population contractions and expansions throughout our evolutionary history, not just a single catastrophic event. The timing itself presents anomalies. Some genetic analyses place the most severe bottleneck earlier, perhaps 100,000, 120,000 years ago. This would disconnect it entirely from the Toba eruption, requiring an alternative explanation. I'm curious, have you ever thought about how your own family might have survived historical catastrophes? What traits or decisions allowed your ancestors to persist when others didn't? Let us know in the comments. The archaeological record reveals another puzzling pattern: the accelerated cultural evolution following the bottleneck period. Around 50,000, 40,000 years ago, human material culture suddenly diversified and complexified in what some call the Upper Paleolithic Revolution. This explosion of innovation included sophisticated blade tools, specialized hunting equipment, elaborate body ornaments, cave art, and figurative sculpture. The timing suggests a potential connection to the bottleneck, but was it cause, effect, or coincidence? Did the bottleneck trigger cognitive or social changes that enabled this cultural flourishing? Or did pre-existing cognitive capacities simply find new expression as populations recovered and competed for resources? Another anomaly appears in the pattern of human dispersal following the bottleneck. Genetic evidence suggests a rapid expansion out of Africa after 70,000 years ago, with humans quickly colonizing Asia, Australia, Europe, and eventually the Americas. This expansion seems counterintuitive immediately after a severe population crash. Why would tiny bands of survivors, presumably struggling to subsist, suddenly embark on history's greatest migration? What drove them to colonize unfamiliar and often hostile environments? The timing of Australia's colonization presents a particularly striking anomaly. Archaeological evidence places humans in Australia by at least 65,000 years ago, requiring maritime technology and navigation skills to cross substantial water barriers. This early date implies that almost immediately after the bottleneck, humans possessed not only the technology to build seaworthy vessels, but also the abstract thinking to attempt voyages to lands beyond the visible horizon. Such capabilities seem incongruous with a species on the brink of extinction. Climate records contain their own contradictions. While some ice cores show significant cooling around 74,000 years ago, others show more modest temperature fluctuations. The pattern suggests regional climate variations rather than uniform global cooling. Marine sediment cores add another layer of complexity. Some show significant disruption around the time of Toba, while others indicate relatively stable conditions. This patchwork suggests that Toba's climate effects varied dramatically by region. Perhaps the most significant anomaly is the human genetic pattern itself. While the bottleneck is evident in our DNA, it appears most severely in non-African populations. This geographic pattern requires explanation. If Toba's effects were global, why would African populations maintain greater genetic diversity? And if the bottleneck preceded the out-of-Africa migration, why would migrating groups leave during a period of environmental stress? One possibility is that the bottleneck primarily affected populations already outside Africa. Small bands that had previously migrated might have faced near extinction, while larger African populations remained more stable. Alternatively, the bottleneck might reflect multiple events affecting different populations at different times. Perhaps separate climate events, competition with other human species, or even pandemic diseases created a complex pattern of population reductions. These contradictions and anomalies don't undermine the evidence for a bottleneck, but they do suggest a more nuanced story. The reality likely involves multiple factors interacting over thousands of years rather than a single catastrophic event. As we examine these inconsistencies, we're reminded that prehistory rarely yields to simple explanations. The story of our near extinction and subsequent flourishing appears to be more complex and perhaps more interesting than initially proposed. Chapter 6. Echoes in Myth. Cultural Memories of Catastrophe. Could ancient myths preserve memories of humanity's brush with extinction? Across cultures, we find recurring stories of world-ending catastrophes, miraculous survivals, and subsequent renewal. Narratives that might encode actual historical events. These stories follow similar patterns: divine punishment, environmental collapse, near-total human extinction, and the survival of a chosen few who repopulate the Earth. The ubiquity of these themes raises the possibility that they reflect cultural memories of actual disasters. Most famous among these is the flood myth, which appears in over 300 cultures worldwide. From the biblical Noah to the Mesopotamian Utnapishtim, the Greek Deucalion to the Hindu Manu, we find remarkably similar accounts of catastrophic flooding and miraculous survival. While these stories are often interpreted as references to post-glacial flooding around 11,000 years ago, they might preserve layered memories of multiple catastrophes. The oldest layers could potentially reach back to the bottleneck period. But flood myths aren't the only tales that might encode memories of the bottleneck. Stories of darkness, cold, and fire from the sky appear in numerous traditions, potentially reflecting experiences of volcanic winter. The Norse Fimbulwinter describes 3 successive winters without summer, leading to the apocalyptic Ragnarok. This pattern matches the expected effects of a supervolcano eruption, years of cold, crop failures, and subsequent societal collapse. Aboriginal Australian traditions speak of a time when the sky fell down, bringing darkness, cold, and death. Some interpretations connect this to astronomical events, but it could equally describe the atmospheric effects of a major eruption. Hindu cosmology describes cosmic cycles including the Kali Yuga, an age of darkness and spiritual degradation. Some scholars have suggested connections between this concept and actual environmental catastrophes in human prehistory. Indigenous traditions from the Americas include numerous references to times of darkness, cold and famine. The Hopi speak of previous worlds destroyed by fire, ice, and flood, with only a small remnant surviving to establish the current world. These mythic accounts can't be treated as literal history, yet they may contain kernels of historical truth. Cultural memories of catastrophic events might have been preserved through oral tradition, gradually transforming into religious and mythological narratives. The time frame presents a challenge. 74,000 years far exceeds the documented range of oral history. Yet some researchers suggest that emotionally charged, culturally central stories might persist longer than ordinary historical accounts. Catastrophic events that threatened a group's very existence would certainly qualify as emotionally charged. The question is whether such memories could persist through tens of thousands of years of telling and retelling. Some anthropologists suggest that myths serve as survival encyclopedias, encoding practical knowledge needed during environmental crises. If so, bottleneck survivors might have deliberately preserved memories of the catastrophe to prepare future generations. These traditions often include not just the disaster itself, but specific survival strategies. They describe which foods remain edible during famine, how to find water during drought, or where to seek shelter from environmental threats. Beyond myths, some researchers point to curious archaeological findings that might relate to the bottleneck period. These out-of-place artifacts and features suggest human adaptations to catastrophic conditions. In South Africa's Pinnacle Point caves, archaeologists found evidence that humans shifted to marine resources around 80,000 years ago. This dietary change might represent adaptation to terrestrial resource scarcity during the bottleneck period. Microscopic analysis of stone tools from this period shows increasing diversity and specialization. This pattern suggests technological innovation in response to changing environmental conditions, precisely what we'd expect from populations under severe stress. Evidence for long-distance trade networks also emerges during and after the bottleneck period. Materials like ochre and marine shells appear at sites hundreds of kilometers from their sources, indicating expanded social networks. These expanded networks might represent a survival strategy. Groups maintaining connections across larger areas could access diverse resources and knowledge, buffering against local environmental failures. Trading partners also provided potential mates outside the immediate group. The timing of these developments is suggestive. Major behavioral innovations appear in the archaeological record shortly after the bottleneck period. This timing hints at a potential connection between our near-extinction and subsequent cultural evolution. Perhaps the most intriguing out-of-place evidence comes from genetic studies of human immunity. Our immune systems show adaptations suggesting ancient encounters with pathogens typically associated with much later agricultural societies. This anomaly raises the possibility that disease might have contributed to the bottleneck. Perhaps pandemic illness, rather than or in addition to climate disruption, drove the severe population reduction evident in our DNA. Another genetic curiosity is the timing of interbreeding between Homo sapiens and other human species. DNA studies suggest that most interbreeding with Neanderthals occurred around 50 to 60,000 years ago, shortly after the bottleneck. This timing suggests a potential connection. Perhaps desperate circumstances drove different human species into closer contact, overriding previous social barriers to interbreeding. The genetic evidence indicates that these encounters were rare but significant. Have you noticed how often catastrophe stories appear in your own cultural background? It makes me wonder if we're somehow hardwired to preserve these warnings through generations. Share your thoughts in the comments. Archaeological evidence from the post-bottleneck period shows increased symbolic expression. Cave paintings, Venus figurines, musical instruments, and elaborate burials. This flourishing might represent more than coincidental timing. Some researchers suggest that the bottleneck itself might have triggered cognitive or social changes. Populations under extreme stress might have developed new forms of cooperation, communication, and symbolic thinking to ensure survival. Others propose that the bottleneck created a founder effect for cognitive traits. If the survivors possessed particular cognitive abilities or tendencies, these would become overrepresented in recovering populations. This hypothesis suggests that modern human psychology, our particular blend of cooperation, innovation, risk-taking and symbolic thinking, might have been shaped by selection pressures during the bottleneck. We are, perhaps, the descendants of those best adapted to catastrophe. A particularly puzzling piece of evidence emerges from genetic studies of brain development genes. Several genes involved in brain growth and neural connectivity show evidence of positive selection around the bottleneck period. These genetic changes might reflect selection for cognitive traits that proved advantageous during environmental crisis. Perhaps specific forms of intelligence, memory, planning, or social cognition made the difference between survival and extinction. Archaeological evidence suggests that successful human groups during this period maintained larger social networks than earlier populations. Sites show increasing evidence of long-distance connections, suggesting that isolation became maladaptive. This pattern appears in the movement of materials, shells, ochre, and high-quality stone, across hundreds of kilometers. Such exchanges indicate social connections spanning multiple ecological zones, providing buffers against localized resource failures. The cognitive demands of maintaining these expanded networks would have been substantial. Individuals needed to track complex social relationships, remember distant landscapes, and navigate between groups with potentially different languages and customs. These demands might have selected for enhanced social intelligence, spatial memory, and linguistic ability, the very cognitive traits that later enabled the development of complex civilizations might have their roots in adaptations to catastrophe. Perhaps most striking is evidence that immediately after the bottleneck, humans began colonizing challenging environments previously avoided. They moved into arid regions, high-altitude zones, and eventually the Arctic, environments requiring technological innovation for survival. This pattern seems counterintuitive. A species barely surviving catastrophe suddenly becomes more adventurous, not less. The contradiction suggests that the bottleneck might have selected for risk tolerance and innovation rather than conservatism. These various lines of evidence, mythological, archaeological, and genetic, suggest that the bottleneck was not merely an event our species endured. It may have been a transformative episode that shaped who we became. The myths that encode these memories serve not just as historical accounts but as warnings and survival manuals. They remind us that catastrophe has happened before and will happen again, that our existence remains conditional rather than guaranteed. As we face new existential threats of our own making, climate change, nuclear weapons, emerging diseases, these ancient memories take on renewed significance. They remind us of both our vulnerability and our resilience. Chapter 7. The Human Paradox, Survivors of Catastrophe. The bottleneck created an evolutionary paradox that defines our species to this day. We are simultaneously the most resilient and most vulnerable of Earth's large mammals, capable of surviving in any environment, yet perilously dependent on complex cultural knowledge. This duality emerges directly from the bottleneck experience. Having passed through the eye of an evolutionary needle, we developed adaptations that enabled unprecedented success while carrying the genetic legacy of our near extinction. Our remarkably low genetic diversity continues to influence human health and development today. We experience population-specific genetic diseases, vulnerability to certain pathogens, and reduced resilience to some environmental stresses due to this restricted genetic heritage. Yet the bottleneck may have also accelerated beneficial adaptations, particularly cognitive and social traits that enhanced survival during crisis. The extreme selection pressure may have favored cooperation, innovation, and complex language abilities. This creates a sobering reality. Our existence as a species might have depended on just a few thousand individuals making the right decisions at critical moments. Had they failed, Earth would now be a planet without humans. The stakes of the bottleneck extend beyond our mere existence to the very nature of human consciousness and society. The cognitive and social patterns that define us might have crystallized during this period of extreme selection pressure. Consider how the bottleneck might have selected for specific cognitive traits. Those who could anticipate environmental changes remember complex spatial information, or innovate solutions to novel problems would have had survival advantages. Similarly, social traits favoring cooperation, information sharing, and group cohesion would have proven adaptive during resource scarcity. Those who could maintain beneficial social connections while managing conflict would leave more descendants. These selection pressures might explain why humans display levels of cooperation rare among primates. Our tendency to share information, resources, and labor, even with non-kin, might be a direct adaptation to bottleneck conditions. The bottleneck may have also accelerated the development of complex language. Under severe environmental stress, precise communication about resources, threats, and complex plans would confer significant survival advantages. These adaptations created a new kind of resilience, not the biological resilience of other species, but cultural resilience. Humans became dependent on shared knowledge, cooperative behavior, and technological innovation for survival. This shift represents a major evolutionary transition from primarily genetic adaptation to primarily cultural adaptation. The bottleneck may have been the crucible in which this distinctly human pattern was forged. The archaeological record supports this hypothesis, showing accelerated cultural innovation following the bottleneck period. New tool technologies, expanded trade networks, and increased symbolic expression all appear within this time frame. Around 40,000 years ago, this acceleration culminates in what archaeologists call the creative explosion, or Upper Paleolithic Revolution. Cave paintings, musical instruments, elaborate jewelry, and figurative art appear across the human range. This timing suggests a potential connection to bottleneck-driven changes in cognition or social organization. Perhaps the very psychological architecture that enables modern human creativity was selected for during our brush with extinction. The stakes of understanding this connection extend into our future. If our cognitive and social traits were shaped by adaptation to catastrophe, this has implications for how we might respond to current existential threats. Are we paradoxically better adapted to crisis than to stability? Does our evolutionary history predispose us toward specific patterns of response to existential risk? And can understanding this history help us navigate current challenges? The bottleneck created not just genetic consequences, but psychological ones. We may carry the imprint of catastrophe in our collective psyche, patterns of thinking and behaving that evolved in response to existential threat. Some psychologists suggest this history manifests in our relationship with existential risk. We oscillate between denial and fatalism, between technological optimism and apocalyptic thinking, patterns that might reflect our evolutionary history. Our fascination with apocalyptic narratives may itself be a psychological adaptation. Maintaining awareness of potential catastrophe, keeping it alive in cultural memory, might have survival value for a species shaped by disaster. The stakes extend beyond psychology to our technological development. The accelerated innovation following the bottleneck established a pattern that continues today, humans responding to environmental challenges with technological solutions. This pattern has proven extraordinarily successful, enabling our species to colonize every continent and reshape Earth's systems to suit our needs. Yet it has also created new existential risks, climate change, nuclear weapons, artificial intelligence, that may exceed our evolved capacity to manage. Here lies the central irony of the bottleneck legacy. The very adaptations that enabled our survival and subsequent dominance may now threaten our continued existence. Our technological prowess has outpaced our wisdom. The genetic evidence of our near extinction raises profound questions about human uniqueness and purpose. Are we merely lucky survivors of a random catastrophe, or does our improbable existence suggest something more? Some interpret the bottleneck as evidence of human exceptionalism, proof of our remarkable adaptability and resilience. Others see it as a reminder of our cosmic insignificance, how easily our species might have joined the long list of evolutionary dead ends. Either way, the bottleneck forces us to confront our contingency. Had circumstances been slightly different, a slightly larger eruption, a slightly colder climate, slightly less adaptive behaviors, Humans would not exist to contemplate their own origins. This reality challenges us to consider what responsibilities might accompany our improbable existence. Having survived when our extinction seemed almost certain, what obligation do we have to ensure our continued survival? The stakes of the bottleneck extend to our relationship with other species. Having experienced catastrophic population collapse ourselves, do we have special responsibility toward other species now facing human-caused extinction? Perhaps most significantly, the bottleneck challenges us to consider our future. Having narrowly survived one existential threat, how should we approach the new threats we've created? What lessons from our evolutionary crucible might guide us now? The parallels between our ancient crisis and current challenges are striking. Both involve global environmental change, resource scarcity, and the need for technological and social adaptation under existential pressure. But there's a crucial difference. The Toba catastrophe and subsequent bottleneck were natural disasters beyond human control. Our current existential threats are largely of our own making, problems created by the very success of our adaptive strategies. This difference creates both responsibility and opportunity. Unlike our ancestors facing Toba's aftermath, we can anticipate and potentially prevent catastrophic outcomes through collective action and technological innovation. The genetic legacy of the bottleneck remains with us, for better and worse. Our reduced diversity creates medical vulnerabilities, but the cognitive and social adaptations forged in catastrophe may provide resources for facing new challenges. As we confront climate change, pandemic disease, and other global threats, we draw on the very traits that evolved during our brush with extinction. Our capacity for cooperation, innovation, and adaptive thinking represents the bottleneck's positive legacy. Yet we must also recognize the psychological patterns that might hinder effective response. Our tendency toward short-term thinking, tribalism, and status competition, possibly adaptive in ancestral environments, may prove maladaptive in facing slow-moving global threats. The stakes could hardly be higher. Having survived one near extinction, we now determine whether our improbable existence continues. The decisions we make in coming decades will shape not just human destiny, but Earth's future. Recent research has identified another consequence of the bottleneck with profound implications. Genomic studies suggest the bottleneck may have accelerated human speciation, separating us more quickly from our hominin relatives. This acceleration might explain the cognitive and behavioral gap between Homo sapiens and other human species. The bottleneck may have compressed thousands of generations of gradual evolution into a brief period of intense selection. If true, this suggests our distinct human consciousness, our particular way of experiencing and relating to the world, may be partly a product of catastrophe. Our minds themselves might have been shaped by our ancestors' struggle for survival. The most startling implication is that without the bottleneck, human consciousness as we know it might never have emerged. The very awareness with which we contemplate our origins might be catastrophe's child. This creates a profound paradox. The disaster that nearly ended humanity may have created what we consider most essentially human. Our creativity, our cooperative tendencies, our capacity for symbolic thought, all might have crystallized in catastrophe's crucible. If this hypothesis is correct, it transforms how we understand human nature and potential. Rather than seeing our psychological traits as inevitable outcomes of gradual evolution, we might recognize them as specific adaptations to extreme circumstances. This recognition carries ethical and philosophical implications. If our minds were shaped by near extinction, what does this suggest about our cognitive limitations, our moral instincts, or our capacity to face new existential threats? As we contemplate our precarious past, the greatest stakes emerge in considering our future trajectory. Having survived one bottleneck through cultural and cognitive adaptation, can we consciously shape our continued evolution? The evidence we've examined suggests both vulnerability and resilience, both reasons for concern and grounds for hope. We are the descendants of those who survived when survival seemed impossible, carrying both their trauma and their triumphs. What happens next may depend on whether we can learn from our evolutionary history, whether the species that survived extinction once can consciously prevent its recurrence. The next chapter of human evolution is ours to write. Chapter 8. The competing narratives. 3 theories of near extinction. As we've explored the evidence for humanity's brush with extinction, 3 competing narratives have emerged. Each offers a different explanation for the genetic bottleneck that nearly ended our species, and each carries different implications for our understanding of human nature. The first and most widely known is the Toba catastrophe theory, which connects our genetic bottleneck directly to the massive supervolcano eruption 74,000 years ago. This theory offers a clean, dramatic narrative with a clear cause and effect relationship. According to this hypothesis, Toba's eruption ejected enough volcanic material to block sunlight worldwide, triggering a volcanic winter that lasted years or even decades. Global temperatures plummeted, ecosystems collapsed, and human populations crashed everywhere, except isolated refugia. The theory's strength lies in its timing and scale. The Toba eruption coincides closely with the genetic bottleneck, and its magnitude certainly matches what would be required to threaten a species with extinction. Geological evidence supports the eruption's massive scale. Ash deposits spanning thousands of kilometers confirm Toba's power, while ice cores record a significant cooling event around this time. However, the Toba theory has faced increasing challenges in recent years. Archaeological sites show human occupation continuing through the Toba timeframe without significant disruption, and climate models suggest the cooling may have been less severe than initially thought. Perhaps most damaging is the lack of bottleneck evidence in other large mammal species. If Toba created conditions severe enough to nearly exterminate humans, we would expect similar genetic signatures in other species. The second major theory proposes that the bottleneck resulted primarily from competition between human species. As Homo sapiens expanded from Africa, they encountered established populations of Neanderthals, Denisovans, and possibly other human species. These encounters would have created competition for limited resources, potentially leading to conflict, displacement, and population crashes. The bottleneck, in this view, represents the outcome of this multi-species competition. This competition theory aligns with the geographic pattern of the bottleneck, most severe in populations outside Africa. It also explains why the bottleneck appears most dramatically in our species rather than other mammals. Archaeological evidence offers some support for this hypothesis. The timing of Neanderthal extinction roughly coincides with the arrival of Homo sapiens in Europe, suggesting competitive displacement. However, genetic evidence complicates this picture. DNA analyses show that rather than simply competing, different human species interbred. Modern non-African humans carry small but significant percentages of Neanderthal and Denisovan DNA. This interbreeding suggests at least some cooperative interactions alongside competition. The reality was likely more complex than simple replacement, involving various forms of cultural and genetic exchange. The third major theory proposes that the bottleneck resulted from climate instability, unrelated to Toba. Between 80,000 and 60,000 years ago, Earth experienced significant climate fluctuations as part of the transition to the last glacial maximum. These fluctuations created rapidly changing environments that would have stressed human populations. Resources would have shifted unpredictably, requiring constant adaptation and occasionally forcing migration. The climate instability theory aligns with paleoclimate evidence showing significant fluctuations during this period. Marine cores, ice cores, and pollen records all indicate substantial environmental changes across multiple regions. This theory also explains the gradual nature of the bottleneck, suggested by some genetic analyses. Rather than a single catastrophic event, populations might have declined over thousands of years as they struggled to adapt to changing conditions. The geographic pattern of human expansion following the bottleneck supports this hypothesis. As populations recovered, they migrated along coastlines and rivers, precisely the environments that would remain relatively stable during climate fluctuations. However, this theory struggles to explain the severity of the bottleneck. While climate fluctuations certainly create hardship, they rarely drive widespread species to near extinction. Other adaptable mammals weathered these same changes without comparable population crashes. Each of these theories has strengths and weaknesses, and the truth likely incorporates elements of all three. Rather than seeking a single cause, we might better understand the bottleneck as resulting from multiple interacting factors. The most compelling synthesis suggests a perfect storm scenario. Climate instability already stressed human populations when Toba erupted, creating a compound disaster that different human species experienced and responded to differently. In this integrated view, pre-existing climate stress had already reduced and fragmented human populations. Toba then delivered a severe additional shock to already vulnerable groups, while competition between human species further complicated recovery. The geographic pattern of survival supports this multi-causal view. African populations, furthest from Toba's direct effects and adapted to their environmental conditions, maintained greater genetic diversity than groups in Asia and Europe. Small bands that had migrated out of Africa found themselves particularly vulnerable, pioneering populations already living at the margins of their adaptive capacity. These groups would have experienced the most severe bottleneck effects. The time frame also supports a multi-causal explanation. Rather than a single moment of near extinction, humans likely experienced several thousand years of population decline, fragmentation, and eventual recovery as they adapted to changing conditions. This integrated perspective helps explain why the bottleneck appears more severe in our species than in other mammals. The compound effects of climate instability, volcanic winter, and interspecies competition created uniquely challenging conditions for early humans. It also explains the paradoxical aftermath, accelerated innovation and expansion following near extinction. The extreme selection pressures would have favored cognitive and behavioral adaptations that later enabled unprecedented success. Perhaps most importantly, this multi-causal view aligns with the complex reality of evolutionary processes. Species rarely face single dramatic selection events, but rather navigate multiple overlapping challenges that together shape their evolutionary trajectory. For our ancestors, navigating this perfect storm required extraordinary adaptability. Those who survived possessed not just physical resilience, but cognitive and social capabilities that enabled flexible responses to rapidly changing conditions. These capabilities, innovation, cooperation, complex language, abstract thinking, later became the foundations of human civilization. In this sense, our greatest achievements may be rooted in adaptations that emerged during our darkest hour. The debate among these theories continues in scientific circles, with new evidence regularly refining our understanding. But the core reality, that humanity experienced a severe population crash that nearly ended our species, remains well established in our genetic record. This bottleneck, whatever its specific causes, represents a pivotal moment in human evolution, a narrow passage through which our species barely squeezed, emerging transformed on the other side. Chapter 9. The Frontiers of Discovery, New Science and Paradoxes. Recent scientific advances have opened new windows into the bottleneck period, revealing complexities and paradoxes that earlier research couldn't detect. These discoveries both clarify and complicate our understanding of humanity's brush with extinction. Ancient DNA technology has revolutionized our view of human evolution during this critical period. By extracting and analyzing genetic material from fossils dating to before, during, and after the bottleneck, scientists can directly observe how our genome changed. These analyses reveal a striking pattern. Certain genes show strong signatures of positive selection during and immediately after the bottleneck period. Many of these genes relate to immune function, brain development, and metabolic regulation. This pattern suggests the bottleneck created intense selection pressure for specific traits. Those who survived and reproduced carried genetic variants that conferred advantages under the catastrophic conditions, reshaping the human genome. Particularly intriguing are the selected genes related to brain development and neural function. Genes like FOXP2, ASPM, and microcephalin show evidence of recent positive selection, potentially influencing cognitive abilities and language. The timing of selection for these genes roughly coincides with the bottleneck and subsequent recovery. This suggests that cognitive adaptations may have played a crucial role in human survival during this period. This genetic evidence creates a fascinating paradox. The disaster that nearly ended humanity may have accelerated the evolution of traits we consider quintessentially human. Our cognitive uniqueness may be partly a product of our near extinction. Advanced climate modeling has also transformed our understanding of the bottleneck period. High-resolution simulations can now recreate ancient climate conditions with unprecedented detail, revealing patterns invisible to earlier research. These models show that climate effects during the Toba eruption were highly variable by region. While some areas experienced devastating cooling, others saw more moderate changes, or even localized warming due to altered circulation patterns. This variability helps explain the archaeological paradox: continuous human occupation in some regions, despite presumed catastrophic conditions. The impact wasn't uniform. Some areas remained habitable refugia, while others became uninhabitable. The models reveal another crucial factor. Seasonal extremes rather than average temperatures may have driven the most severe human impacts. Even if annual average cooling was moderate, unusually harsh winters or dry seasons could devastate human populations. This insight resolves the paradox of why humans might have suffered more severely than other mammals. Our species' reliance on cultural adaptations and technological solutions may have become a vulnerability when conditions changed too rapidly. I'd love to know, does learning about humanity's near extinction make you feel more pessimistic or optimistic about our species' future? Let us know your thoughts in the comments below. Another scientific frontier involves ancient pathogen DNA. New techniques can identify traces of prehistoric epidemics by detecting pathogen genetic material in ancient human remains or through genetic signatures of immune adaptation. These analyses suggest that ancient humans encountered novel pathogens during the bottleneck period. As climate changed and populations migrated, humans likely contacted unfamiliar disease environments, potentially triggering epidemics. This evidence raises the possibility that disease contributed to the bottleneck. Populations already stressed by environmental factors would have been particularly vulnerable to novel pathogens. The geographic pattern of these immune adaptations creates another paradox. Some protective genetic variants appear most frequently in populations that remained in Africa, while others concentrate in groups that migrated outward. This pattern suggests different pathogen challenges in different regions, with selection favoring region-specific immune adaptations. The bottleneck may have played out differently across populations depending on their particular disease environment. Advanced archaeological techniques have also transformed our understanding of this period. Microscopic analysis of stone tools, residue analysis of ancient hearths, and isotope studies of human remains reveal subtle patterns invisible to earlier research. These techniques show that dietary adaptations varied dramatically during the bottleneck period. Some groups shifted toward marine resources, others specialized in hunting megafauna, while some intensified plant food exploitation. This diversity creates another paradox. Human cultural adaptations became more varied precisely when population size declined. Rather than convergent evolution toward a single optimal strategy, bottleneck survivors pursued multiple adaptive pathways. This pattern challenges simple models of human evolution. Rather than a linear progression toward modern behavior, we see a complex branching pattern of diverse adaptations to specific local conditions. The most successful strategies apparently combined flexibility with specialization. Groups that maintained diverse resource knowledge while developing specialized technologies survived better than those committed to single strategies. This insight helps explain a central paradox of human evolution: why our species survived when other intelligent human species did not. Homo sapiens may have possessed a unique balance of cultural conservation and innovation. Genomic studies of contemporary human populations have revealed another surprising pattern. Certain isolated groups, particularly in Africa, preserve genetic lineages that diverged before the bottleneck, maintaining diversity lost in most other populations. These populations, including some Khoisan groups in southern Africa and certain Central African forest communities, essentially represent genetic time capsules. Their genomes contain diversity eliminated elsewhere by the bottleneck. This discovery creates both a scientific opportunity and an ethical challenge. These populations provide crucial windows into pre-bottleneck human genetic diversity, yet face threats from displacement, assimilation, and exploitative research practices. Another paradox emerges from studies of Neanderthal and Denisovan DNA. While these species also experience population declines, their genetic diversity remained proportionally higher than that of Homo sapiens during the same period. This pattern suggests these species may have been better adapted to cold conditions or more resilient to specific environmental stresses. Yet they ultimately went extinct, while Homo sapiens survived and thrived. The resolution to this paradox may lie in differences in social structure and cultural transmission. Homo sapiens may have maintained more extensive social networks, preserving and sharing cultural knowledge even as populations declined. Archaeological evidence supports this hypothesis, showing that Homo sapiens maintained long-distance trade networks during the bottleneck period. Materials moved hundreds of kilometers between groups, suggesting information and innovation also traveled these networks. The most profound paradox to emerge from recent research involves the relationship between the bottleneck and human creativity. Archaeological evidence shows an explosion of symbolic behavior and technological innovation following the bottleneck period. Cave paintings, figurative art, musical instruments, and increasingly complex tools all proliferate in the archaeological record after 50,000 years ago. This creative explosion follows suspiciously close after our brush with extinction. This timing suggests the bottleneck may have played a causal role in human creative evolution. The extreme selection pressures may have favored cognitive and social adaptations that later enabled unprecedented cultural innovation. If true, this creates a profound philosophical paradox. Our greatest achievements may be rooted in our greatest catastrophe. The very faculties that enable human art, science, and civilization may have emerged as adaptations to near extinction. Recent neurobiological research adds another dimension to this paradox. Studies suggest that moderate stress can enhance cognitive performance and creative problem-solving, while severe stress impairs these functions. This relationship creates a narrow, optimal zone, enough stress to stimulate innovation, but not enough to trigger cognitive shutdown. The bottleneck may have created precisely these conditions, selecting for those who remained creative under pressure. The picture emerging from these diverse scientific frontiers is one of remarkable complexity. The bottleneck was not simply an event our species endured, but a transformative process that helped create what we consider distinctly human. This perspective transforms how we understand both our past and our future. If crisis shaped our cognitive evolution once, how might current and future challenges continue to shape our species? Chapter 10. The Great Revelation, Catastrophe as Catalyst. Throughout this exploration, we've been circling a profound and disturbing possibility. What if humanity's defining characteristics, our creativity, our cooperativeness, our cognitive flexibility, aren't merely traits that helped us survive catastrophe, but products of catastrophe itself? The evidence increasingly points toward this revolutionary conclusion. The bottleneck didn't just test our existing capabilities, it helped create them. The humans who emerged from this evolutionary crucible were fundamentally different from those who entered it. This transformation appears in multiple dimensions. First, at the genetic level, we see strong selection signals for genes related to brain development during and immediately after the bottleneck period. These genetic changes potentially enhanced neural connectivity, language processing, and social cognition. Second, archaeological evidence shows rapid behavioral changes following the bottleneck. Complex symbolic expression, technological standardization, and long-distance exchange networks all proliferate in the archaeological record after this period. Third, The geographic pattern of human expansion following the bottleneck suggests new adaptive capabilities. Humans rapidly colonized extremely diverse environments, from tropical rainforests to Arctic tundra, displaying unprecedented ecological flexibility. These patterns converge on a remarkable conclusion. The bottleneck functioned as an evolutionary accelerator. By drastically reducing population size and creating extreme selection pressure, it compressed thousands of generations of gradual evolution into a relatively brief period. This acceleration affected both genetic and cultural evolution. Beneficial genetic variants spread rapidly through the small surviving population, while adaptive cultural innovations diffused quickly through necessity-driven social networks. The bottleneck essentially created an evolutionary pressure cooker. Only those with exceptional abilities to innovate, cooperate, and adapt survived to reproduce, rapidly shifting both the genetic and cultural composition of the human population. This process selected for a suite of cognitive and behavioral traits that define modern humanity. Enhanced working memory, theory of mind, linguistic capability, and technological creativity all appear to have flourished during this period. Most significantly, the bottleneck may have selected for a uniquely human form of cultural transmission. The ability to learn and share complex information across generations became essential for survival under rapidly changing conditions. This capacity for cumulative cultural evolution, building on previous innovations rather than reinventing solutions each generation, represents humanity's greatest adaptive advantage. It emerged as a necessity when population density plummeted during the bottleneck. In smaller groups, specialized knowledge becomes vulnerable. If the only person who knows how to make a particular tool dies, that knowledge is lost. The bottleneck would have strongly selected for improved methods of preserving and transmitting cultural information. This selection pressure may explain the explosion of symbolic behavior following the bottleneck. Cave paintings, figurines, and other symbolic expressions may have originated partly as information storage systems, external memory devices for critical knowledge. Similarly, standardized tool production techniques emerged during this period. This standardization facilitated knowledge transmission across generations and between groups, creating resilient cultural repositories that could survive individual deaths. The bottleneck likely also selected for enhanced cooperation and social bonding. In crisis conditions, groups that could maintain cohesion and share resources would survive better than those fragmented by conflict. This selection for cooperativeness appears in our biology. Humans show unusually high levels of oxytocin sensitivity and neural responses to social cues compared to other primates. These traits facilitate the intense social bonding that became crucial during population collapse. Perhaps most significantly, the bottleneck may have selected for long-term thinking and planning. When environments become unpredictable, the ability to anticipate future conditions and prepare accordingly confers significant survival advantages. This capacity for mental time travel, imagining future scenarios and planning responses, represents another distinctly human trait that may have been enhanced during this period. It underlies everything from food storage to technological innovation. The great revelation, then, is that we are not merely descendants of catastrophe survivors, we are catastrophe's children. The distinctly human mind, with its unique blend of creativity, sociality, and foresight, may be largely a product of near extinction. This perspective transforms how we understand human nature and potential. Rather than seeing our cognitive and social traits as inevitable outcomes of gradual evolution, we recognize them as specific adaptations to extreme circumstances. This recognition carries profound implications. First, it suggests that crisis can function as a catalyst for evolutionary change. Periods of stability may actually slow innovation, while existential threats can accelerate both genetic and cultural evolution. Second, it suggests that our cognitive architecture evolved specifically to solve survival problems under extreme conditions. Our minds are optimized for crisis response rather than long-term equilibrium. This may explain certain paradoxes of modern human behavior. Our remarkable ability to respond to immediate threats alongside our struggle to address slow-moving, abstract challenges like climate change, makes sense from this evolutionary perspective. Third, it suggests that human consciousness itself, our particular way of experiencing and relating to the world, may be partly a product of catastrophe. Our subjective experience may be shaped by adaptations that evolved during our brush with extinction. Most provocatively, this perspective suggests that without the bottleneck, modern human consciousness might never have emerged. Had our species continued along a gradual evolutionary trajectory, without facing near extinction, we might think and feel very differently. This creates a profound paradox. The disaster that nearly ended humanity may have created what we consider most essentially human. Our creativity, our cooperativeness, our capacity for symbolic thought, all might have crystallized in catastrophe's crucible. As we face new existential challenges, climate change, nuclear weapons, artificial intelligence risks, this evolutionary history takes on renewed relevance. We are the descendants of those who survived when survival seemed impossible. This legacy suggests both vulnerability and resilience. We carry genetic and cultural adaptations forged during crisis, potentially equipping us to face new threats. Yet our evolved psychology may also create blind spots to certain types of challenges. Understanding this evolutionary history offers practical insights for navigating current existential risks. By recognizing both the strengths and limitations of our crisis-adapted minds, we can design better systems for addressing long-term, complex threats. For instance, our evolved psychology responds strongly to immediate visible threats, but struggles with abstract, gradual dangers. This explains our difficulty mobilizing against climate change compared to our rapid response to pandemic disease. By acknowledging these psychological tendencies, we can create institutional and technological systems that compensate for our evolved limitations. We can build decision-making structures that leverage our crisis response capabilities while mitigating our cognitive biases. The bottleneck's legacy thus offers not just an origin story, but a survival manual. By understanding how catastrophe shaped us, we gain insight into both our remarkable capabilities and our dangerous blind spots. Perhaps most importantly, this perspective offers a certain cosmic hope. If humanity's greatest capacities emerged from our darkest hour, perhaps our current challenges might similarly catalyze positive transformation. While we should never invite catastrophe, we can recognize that crisis creates unique possibilities for rapid adaptation and innovation. The pressure of existential threat has previously accelerated both our genetic and cultural evolution. This is not to romanticize suffering or minimize the tragedy of population collapse. It is merely to recognize that evolution often advances most rapidly under pressure, and that humanity has previously emerged transformed from the brink of extinction. The great revelation, then, is that catastrophe functioned as both test and catalyst. It eliminated most human lineages while accelerating the development of traits that would eventually enable unprecedented success for the survivors. We are the inheritors of this double legacy, the trauma of near extinction and the cognitive transformation it triggered. Understanding this history helps us recognize both the fragility and the remarkable resilience of our existence. As we close our exploration of humanity's brush with extinction, we return to the image we began with. A small band of humans standing at the edge of a cliff face 80,000 years ago, their future and ours hanging by the thinnest of threads. Had just a few more of them perished, had the population dropped below the minimum viable threshold, our species would have joined the long list of evolutionary experiments that nature tried and discarded. We would not exist to contemplate our own origins. This realization confronts us with the profound contingency of our existence. We are here because a small group of ancestors made the right decisions at critical moments, adapting to catastrophic conditions that eliminated most human lineages. Their legacy lives in every human cell, in the genetic bottleneck signature we all carry, in the cognitive adaptations that emerged from crisis, in the cultural innovations that flourished as populations recovered. We are, in a very real sense, catastrophe's children. This perspective invites both humility and wonder. humility in recognizing how close we came to non-existence, and wonder at the remarkable adaptations that emerged from this evolutionary crucible. As we face new existential challenges of our own making, our bottleneck history offers both warning and inspiration, warning about our vulnerability and inspiration from our ancestors' resilience in the face of near extinction. Perhaps this is the most important lesson. We have faced the abyss before and survived, not through any cosmic guarantee, but through adaptation, cooperation, and innovation, the very traits that catastrophe helped create. In this sense, the night humanity almost disappeared lives on within us, both as ancient trauma and as the source of our greatest capacities. It reminds us that our existence remains conditional rather than guaranteed, dependent on wisdom born in our darkest hour. If you found this journey through humanity's past enlightening, consider subscribing to our channel for more explorations of the forgotten chapters of our collective story. Together, we'll continue uncovering the mysteries that shaped who we are and who we might become.